Okay, great. So once again, good afternoon, everyone. Today I would like to present the results of my investigation. The title is Mechanical Stimulation decrease Auxin and Gibberellic acid synthesis, but does not affect Auxin transport in axillary buds, but it also stimulates peroxidase activity. So, in the beginning, I would like to tell you and introduce to you the topic and the source of my scientific interest. Thigmomorphogenesis. What is thigmomorphogenesis? It's a natural event, and this event is the reaction of plants of some mechanical stimulation, natural mechanical stimulation, like wind. Usually regular wind. It doesn't have to be strong, but regular wind, rain, or some mechanical obstacles like walls of the buildings. And plant has to adapt to these environmental factors, and that's what plant is doing. What is the reaction of the plant? Is to modification of plant architecture. Usually it is harassment of internode growth, increase of side shoots, branching numbers. Also, it may be the response, and it is, surely it is, we know that. There is a plant response on physiological and of course molecular level. Like there are maybe differences, like decrease of auxin synthesis, of endogenous gibberellin synthesis, like GA1 or GA3. It may be an increase in synthesis of cytokinins, and also there was a hypothesis that mechanical stimulation may arrest the transport of endogenous auxins. Continuing the topic of plant response, just on a environmental view level, what can we see? So usually plants reaction may be very fast, like in mimosa, but most of the plants, their reaction is quite slow. So we don't see that reaction immediately, just in a period of time, like after several days or weeks or even months. Of course, the reaction may differ also during the cultivars. So the same genus, but different cultivars. And there are several hypotheses which claim that mechanical stimulation cause increase in radial expansion, decreases plant growth, and on the cellular level, it may arrest the auxin synthesis or their transport. The interest of thigmomorphogenesis, this phenomena is not new. Jaffe interested and published first the results and also created that term, thigmomorphogenesis, in 1973. So he observed the reaction of plants, mostly trees, for environmental factors like wind or rain. And in early 90s, some of the researchers started to continue the research, mostly on horticultural level, agricultural and horticultural level. But that branch of science did not develop. It was arrested. And in second decade, so in 20s of current century, this event, this phenomena, again was the scientists interested in this phenomena, and it started developing. To continue, the plant reaction is usually increasing thickness of leaves, of stems, but sorry, decreasing decreasing the area of leaf. Also, touch genes. So scientists started to interest in genes which start their expression as a reaction for touching, for mechanical stimulation. Also, the ethylene is releasing during mechanical stimulation. And that's what I would like to present. So, polar transport of auxins, it may be arrested. Also, activation of peroxidase, endogenous peroxidases, may increase, and it may arrest auxin synthesis. And also, mechanical stimulation may affect the decrease of Gibberellic biosynthesis in several plants. So, some of a little bit of theory. So, what is auxin transport in plants? So, usually there are two pathways of auxin transport. The first one is not connected with the polar transport of auxins, so it is not active. It is just transported away from the source tissues, usually young leaves, stem apical meristem, by an unregulated bulk flow in the mature phloem. But another one is polar auxin transport. So this is active transport. It is regulated by carrier-mediated cell-to-cell directional transport by the proteins in a vascular cambium. Again, from the shoot apical, the stem apical meristem to root apical meristem, so to root apex. And there are many of the proteins which transport the carriers, which transport auxins. Many of them, they are discovered. This is the most popular, the most common in researching studies usually is auxin number one. So aux number one, lax number one, and they called that these carriers are influx. So usually they are in a cell. They come from cell to cell, and other ones are efflux, and the most popular is PIN, usually PIN 1. Of course, these auxins are responsible for several development processes in plant. PIN is like vascular development, phyllotaxis, vine formation, embryogenesis, lateral organ formation. And here is just a slide which shows in which developing processes of plant development influx auxins are involved. Here in this slide, you can see non-polar transport, so just passive transport of the auxin, and polar auxin transport, which is active transport. And it's regular transport of the auxins by proteins. Why I show this slide? This slide is shown because the researchers involved in process of thigmomorphogenesis, they were claiming that touching of the stem meristems in young tissues, young stems, it may work similarly like decapitation of the shoot apical meristem. So what people claim, what researchers claim, what will happen? So they claim that not decapitation but touching will activate auxin transport in axillary buds, and plant will be increasing their radial growth. Here in this picture, you can see it. You can see that the transport of pin and the passive transport of auxin is decreasing, and the active transport of pin is increasing, and also the same is happening here. And the reaction of the plant is really quick. So on physiological molecular level, it's quite quick. So what is the hypothesis? So first hypothesis was that mechanical conditioning is arresting auxin synthesis or polar transport. We were working on petunia, bedding plant petunia, and we were making mechanical stimulation on different stress, like touching 80 times, 120 and 160 times touching per day. And we were observing and making analysis of plants 7 days after starting of touching, 14 days, 30 days, 56 and 71 days. So what is interesting, that plants started decreasing their growth usually on term 3. So it was 30 days after mechanical stimulation began. Of course, this process started earlier, but what we could just see that was the significant difference between control plants and this mechanically stimulated. Usually it was close to the 30 day. The same is presented of this diagram. So 30 days we could really see that plants were shorter. And what happened with the synthesis of auxins? So with the synthesis of auxins, it happened nearly the same. So on 30 days of the experiment, we could see that synthesis of auxin in shoot apical meristems, depending on stress intensity, is really decreasing. We couldn't see it in roots. it was really well seen in shoot apical meristems. And what about the polar transport? So that's what you could see. Here you could see control plants, and here you could see the plants which were stressed 160 times per day. So here you have the response of plants on aux, lax, and pin. And that's what we could see. So we could see the presence of aux, lax, and pin proteins in apical meristems, shoot apical meristems, but it wasn't present in axillary buds. And we saw the same situation in plants which were stimulated 160 times per day. So we could see it in apical meristems, but we couldn't see them in axillary buds. Nearly the same situation was present with gibberellic acid number 3. So we could see decrease of this gibberellin in plants stimulated 120 and 160 times per day for 14 and 30 days after the stress started. Why we could see so different results on term 5? Because on term 5 we stopped the experiment, the stimulation, and plants were growing 2 weeks before stimulation, and that's what happened. Plants started growing very fast, especially these plants which were stimulated. Hypothesis 2 is that peroxidase activity during manual stimulation, it causes lignification of cell walls and the same arrests growth of the plants. And that was interested. So we could see the ambient activity of peroxidase in shoot apical meristems, but 14 days after the experiment started, we could see significant increase of peroxidases in roots. What we could see here on histological photographs, so we could see that control plants which were not stimulated, very young tissues, we could not see strong lignification or beginning of lignification of usually on of vascular veins. But in plants which were stimulated 160 times per day, it was really clear. We could also see that colonchema is really well developed. So what are the conclusions? So in current research, we confirmed that over a longer period of time, mechanical stimulation, it's going to change and arrest growth dynamics and auxin synthesis in petunia, but after longer period of time. Mechanical stimulation does not arrest basipetal auxin transport, polar auxin transport, but also just a passive. And in current research, we proved that petunia plants subjected to mechanical stress of 160 times per day, it clearly reduced their growth, while they increased their diameter, and this is said with the production of bedding plants such as petunia, just in horticulture. The increase in growth dynamics in petunia after the cessation of mechanical stress is a clear physiological response of plants to return to a state of homeostasis. So this is on term 5, that plants were growing 2 weeks without any stimulation, and the homeostasis on a physiological level, and just on growth plants started growing. So this is natural response of plants. So here is the references, and thank you very much for your attention.
Thank you, Dr. Akar. That's a great presentation. Now the session